Acid-base concept. There are three major definitions of acids and bases have influenced the thinking of chemists. In 1884, a scientist known as Arrhenius formulated the first definition of the acid-base concept, and in 1923, two scientists known as Bronsted and Lowry developed the second definition, whereas in 1916 the third definition was developed by the Lewis. So now let's come to the first definition that is proposed by the Arrhenius in his doctoral dissertation, and that was the revolutionary definition to such an extent that he was almost denied his PhD. However, in 1903 he received the Nobel Prize in Chemistry for his theory, that is the Arrhenius acid-base concept. His theory states that the stable ionic compound that is soluble in water will break down or dissociate into its component ions. So this dissociation or ionization of a compound in water led to the Arrhenius definition of acid and base. So an acid is a substance that when added to water increase the concentration of hydronium ion. So an acid is a substance that increase the concentration of hydronium ions, because the Arrhenius theory regarded the acid-base reactions as occurring only in water, and he also called the hydronium ion as hydrogen ion. So here hydrogen ion is a proton or hydrogen that is electron deficient. So according to this theory, an acid is a substance when added to the water, it increases the concentration of hydronium or hydrogen ion, which is electron deficient. So a base is a substance that when added to water, it increases the concentration of the hydroxide ion. So according to this explanation, we can summarize the definition of the Arrhenius acid, that is an Arrhenius acid is a source of hydrogen ions or the protons or the hydronium ions, whereas the base is an Arrhenius base when it acts as a source of hydroxide ions. So this theory, that is known as Arrhenius acid-base theory, provided a good start towards the understanding of the acid-base chemistry, but it proved much too limited in its scope because it is applicable on the ionic compounds that are soluble in water only, whereas the second definition is independently given by two scientists known as Bronsted and Lowry, who gave a more general acid-base definition than that of the Arrhenius. Although they considered reactions other than those that takes place in the aqueous solutions, but they still said that acids were molecules that donate the hydrogen ion, so they can increase the concentration of hydrogen ion within the solution of the substances containing the acids. For example, acids like HCl and sulfuric acid can donate the proton to the solutions. However, they broadened the definition of bases to include any compound that accepts a proton. So the Arrhenius acid and the Bronsted-Lowry acids are the proton donors, whereas the Bronsted-Lowry base is a proton acceptor. The basis of their acid-base definition is that in a reaction, a proton transfers between the reactants. Thus, acids involving a transfer of proton or the hydrogen ions are sometimes called the proton acids. So according to the Lowry-Bronsted definition, an acid is any molecule or ion that donates a proton to another molecule or ion. So here the hydrogen ion is donated by HCl to hydroxide ion of this base to make the water molecule. And a base is any molecule or ion that receive that proton. So here the hydroxyl ion that is actually generated from the base when it was dissolved into the water, and this acid was dissociated to the hydrogen and the chloride ion. So here the proton that is generated from the acid have been donated to the base that is accepting this proton. So here this molecule of HCl that generated the hydrogen ion and the chloride ion is donating the proton to the system, whereas the sodium hydroxide, which is dissociated into the sodium and hydroxyl ion, is accepting the proton. So the first substance is an acid, that is the Bronsted-Lowry acid, and the second one is the base, that is Lowry-Bronsted base. So simply we can call a Bronsted-Lowry acid is a proton donor, whereas a Bronsted-Lowry base is a proton acceptor. So here the hydrogen chloride or hydrochloric acid is known as proton donor, and sodium hydroxide is known as proton acceptor. Now let's check out another example for the Bronsted-Lowry acid and bases. For example, we have sulfuric acid that is acting as the proton donor, and ammonia, which is acting as proton acceptor. So here the proton from the sulfuric acid will be donated to the ammonia, which becomes the proton acceptor. So we get the ionic species that is known as hydrogen sulfate ion and the ammonium ion. Now let's check out another example. Again we have HCl as acid and primary amine as base. So this one is proton acceptor, so this hydrogen ion will be, or the proton hydrogen ion is also known as proton, which is electron deficient. So this proton is donated to the primary amine to make the chloride ion and the alkyl ammonium ion. In order to elaborate the concept, let's take another example. For example, we have sulfuric acid, which can donate the 2 protons, and we have an organic compound which is the acting as proton acceptor. So we have HSO4 minus and CH3 and CH3. So there is a positive charge because carbon must have 4 bonds. So here it have 3 bonds, so it must have a positive charge. So in all above cases, when an acid or a base react with acid or acid react with base, and or we can say when an acid and a base react with each other, the reactants and the products are in equilibrium with each other. It means the number of protons that are transferred from the acids to the bases are equal to the number of protons that are transferred back. So it indicates that these are the equilibrium reactions, and that is the reactant on the left side of the reaction are reacting and forming the products, and the products on the right side are also reacting and forming the starting reactants. So for the forward reaction we call them acid and base, but for the backward reaction, that is the reaction from right side, these species are known as conjugate acid and conjugate base. And according to the definition, an acid must donate the proton and base must accept the proton. So here the proton is accepted by this species, so this species is acting as conjugate base, and this one is acting as conjugate acid. And this is true for the other examples given here. So this species and this one is also acting as conjugate base, and these two are also acting as conjugate acids. Now let's discuss this example. A hydrogen of sulfuric acid is the acid, and the nitrogen of the ammonia is the base. Why? Because the hydrogen is donating the proton and this nitrogen is accepting the proton. They react to form hydrogen sulfate anion and the ammonium ion. So the ammonium ion is the conjugate acid of ammonia, and the bisulfate ion is the conjugate base of the sulfuric acid. So the Lowry Bronsted defined acids and bases in a broader scheme than the Arrhenius, but the concept was similar. And the third scientist, known as Lewis, who noted that there are a number of reactions that look like acid-base reactions but do not involve the transfer of a proton, Instead, they involve the interaction of a pair of non-bonding electrons. From that observation, he defined an acid as a molecule that forms a covalent bond by accepting a pair of electrons, and a base as a molecule that forms a covalent bond by donating a pair of electrons. So we can simplify his theory as a Lewis acid is an electron pair acceptor, whereas a Lewis base is an electron pair donor. That's because a Lewis acid accepts a pair of electrons. Chemists call an electrophile. So, acid, also known as electrophile, from the Greek meaning lover of electrons or electron loving. They called a base a nucleophile or lover of nuclei because it donates the electron to a nucleus with any empty orbital. In a reaction, a nucleophile seeks a nucleus or a positive charge, and an electrophile seeks electrons or a negative charge. Fundamental to the chemistry, all reactions of an acid with a base, more commonly known as electrophile and nucleophile, attacking reactions usually observed in organic chemistry. So now let's denote an acid that is the electron deficient. So it is known as electrophile. So it is also known as acid that reacts with a base having empty space to make a bond through coordinate covalent bond. It means it have lone pairs of the electrons, or it is electron rich or negatively charged. So here we can see that a base have two electron pairs that are not bonded with any of the atom, and these two electron pairs can be donated to the electrophile or acid. So here the acid is acting as the electron acceptor and this base is acting as electron donor. So with donation of these two electrons, so minimum two electrons are important for the formation of a single bond. A single bond is formed between A and B. Now let's discuss another example. For example, we have a boron trifluoride, and it's a neutral molecule, but it have empty orbital. This empty orbital can accept the lone pairs that are not bonded with any other atom, and these lone pairs are present in the outermost orbital of the nitrogen. Nitrogen have 5 electrons in the outermost shell, and each of the 3 electrons are shared with the electrons of hydrogen. So they are already bonded with 3 hydrogens, but it have an extra lone pair which is not bonded with any other atom. So these lone pairs can be donated to the empty orbitals of the boron, which accept the electrons, and a bond is formed that is known as coordinate covalent bond. So as the boron is accepting the electron pairs, so it have a negative charge, and this one is donating the electron pair, so it get the positive charge. And usually this kind of curved arrow is used to show the movement of electron from the electron donor to the electron acceptor, or donor is also known as base and the acceptor is known as acid.